Hi all, I'm Mr. Yeager for chemistry. We are now getting into the last part of this unit on periodic table and the arrangement and organization of electrons with electron configuration. Again, this PowerPoint presentation was created by another very good chemistry teacher, and I'm using it for the presentation today. So with this, we are getting to the point where we are really trying to clearly show where the electrons are located, or at least best possibility of where they are located in the atom. And this is very much pattern oriented. All right, there is kind of a little kind of cheat sheet diagram we're going to use to help us out, but the periodic table shows all of these patterns as well. It will seem very weird at first. It'll make possibly zero sense to sit there and be like, why are we using the letters S, P, D, F? All right, we just do. Is basically going to be your answer for now. If you go into college chemistry, you can understand where they actually get those names from. But we are just interested in writing out the actual arrangement of all the electrons, because we just finished the flame test and we know that they're in these energy levels, and we want to make that clear. So here we go. So looking one more time at the modern model of the atom is the quantum mechanical model. We've been kind of using the Bohr model as the clearest kind of picture of the model of the atom, where you have the nucleus and then the electrons are orbiting around the nucleus. Again, that only works well with the hydrogen atom because it's just the one electron, and we know that there's only one electron going around the nucleus. But if there's more than one electron, while the Bohr model would kind of say that they are then orbiting in a set arrangement around, like going in a circular pattern around the nucleus, that's not true. These electrons are moving very quickly, and we can only give probable locations of where they are versus exact locations as the Bohr model would like for us to be able to predict. So it's more about, again, creating this model where we have very strong probabilities that the electrons are here, but because they are getting excited and they are moving between energy levels at different times, it's better if we make this as a probability versus an exact. Now, it'll kind of look like we're setting it up exact, all right? But even within that frame, there's still a little bit of, I don't want to call it error, but some wiggle room to say they're very likely in this area. All right, so that gets us to what's called electron configuration, all right? So as we kind of talked about a little bit already, electrons are arranged where we add them inside, like closest to the nucleus first, and then we start adding, as those energy levels on the inside fill up, we start adding electrons on farther and farther and farther out energy levels. And we always do that, starting from hydrogen, going all the way to the very last element on the periodic table, number 118. I don't even know, it probably has a name now, but I still have one of the unknown ones written there. But it works but every single atom wants those electrons to be on the lowest energy level first before you go up to higher energy levels. Within those energy levels, we have what are called subshells. And we label these S, P, D, and F. And I guess I will say, they all relate to a shape in terms of what type of arrangement and probability shape that those electrons are moving around in that energy level. So like S stands for spherical, P stands for parabolic. The funny thing is, I think like F stands for fundamental, which I'm like, I don't know what shape that is. But that's basically what you're looking at here with it. And again, if you get to a higher level chemistry, you do get more detailed with how to place those electrons in those different areas. But for now, we have these four subshells, S, P, D, F, okay? And there are a specific number of electrons that I can put into those levels. This is the maximum number I can hold. So S can hold a maximum of 2 electrons, P can hold a maximum of 6, D 10, and F 14. While that seems extremely random, the periodic table, and that's the big thing to understand, the periodic table absolutely illustrates the pattern of 2, 6, 10, 14. And we'll see that when I can pull up a periodic table in a moment. Okay? All right. So how do I then add these different electrons to these subshells? Okay. And so what we have is this thing's called an off-ball diagram. At least that's what I've heard this called as, an off-ball diagram. And Off-Ball was a scientist that helped kind of create this pattern, and he created a rule that said you always have to add electrons to the lowest energy level first. So that's what this is trying to show you. So let me kind of explain this a little bit more. You see that it says 1s. The first big number is the energy level that the electron is in. So this would be that the electron's in the first energy level in the s subshell. And then what we'll do is we're going to add an exponent. I'll put a 2 right there. And this little exponent or superscript represents the number of electrons in that subshell. So what we would say here is there are 2 electrons in the S subshell in the first energy level. That is what we're saying with it. Okay? And you don't need to know anything really much more than that other than that's the meaning behind it. Okay? So this little kind of diagram that you have is meant to be a way for you to help you understand how to fill up the electrons into the atom, especially as it gets larger and larger and larger elements, how you do it, and you do it the same way over and over, and you always start at the bottom. Okay? So you can see, I mean, if you didn't have this and you had to write this out, what you do is you write 1s at the bottom, 2s, 3s, 4s, 5s, 6s, 7s. Then you start at 2p, and you go 2p, 3p, 4p, 5p, 6p. Then you start in the third row, 3d, and then fourth row, 4f and 5f. All right? So that's the arrangement of those kind of boxes. What you then do is you draw arrows from the bottom right-hand corner of the edge of this pattern. So down at the right, down at the right, down at the right, et cetera, et cetera. Sorry, there's one right there. Down at the right. Okay, I know it's kind of tough to see a little bit. Sometimes it juts in a little bit. Okay, down at the right. And the idea is we go up and through that energy level. And when you have that particular box or energy level, you write that one down, if that's the one you're passing through. And maybe this makes sense when we actually start using some elements with it, so you can see what we're doing here. So that would be 1s. Then you can see we're going to use the second arrow, and we're going to fill in 2s. The third arrow is finally where you see where we start building a little bit more of a pattern. We're going to go through 2p, and then we go through 3s. And then you keep going. Then we would go through 3p, and then 4s. And then we finally hit D, 3d, 4p, 5s, and so forth. You keep going. You can see we got to do a whole nother row before we or diagonal before we finally get to 4f. And because that's going to be down near the bottom of the periodic table. There's going to be a lot of electrons involved. But this is what you follow for every single element. You always start at 1s. That's what I should see over and over again when we're building up these atoms, these elements, the electron configurations. So I'm going to skip that first part and jump straight to this one first, the electron configuration notation. So this is what I was talking about, that you're going to eventually start writing out these electron configurations. All right? And again, it looks very random. I don't expect you to completely get it until you've tried probably like a half dozen of them, and then you're going, okay, I can start seeing this pattern. Okay? One alone does not make sense, usually, almost to anybody. All right? You need to do 3, 4, 5, 6 to really understand and maybe start seeing the pattern, and some of you might need even more than that to understand the pattern. But you will see and start following this pattern. It has to be repetitive. If it's not repetitive, you're doing it incorrectly. All right? So let's start looking at some of these elements that we got. So the first one we got is nitrogen. Sorry, I'm going to look at it. Nitrogen, manganese, and argon. All right? So I'm going to go back to my diagram. Nitrogen, manganese, argon. All right. So the way this would work is I would look at my periodic table. Let's start with nitrogen. Okay? And I'm doing electrons, and we're assuming all the atoms right now are neutral. So I look at nitrogen, and I need to know how many electrons I have. All right? Well, nitrogen has an atomic number of 7, which means it has 7 protons, which means it has 7 electrons.
I think so.
Yep. It has 7 electrons. Okay? So I need to figure out how to place 7 electrons into the electron configuration. So what I'm doing is I'm starting down at the bottom. And so the electron configuration for nitrogen would be 1s. And I can get 2 electrons in 1s. So I'm going to put 1s2. Okay? I mean, you can even kind of go back and kind of think about this, that all these could be maximum 2. They could be 1 or 2. Okay? So 1s2. All right? But that's only 2 of the electrons. So I still have 5 more electrons to place. So I go to the next arrow and I go through 2s. So I'm going to write 2s. I have 5 electrons still, but I can only place 2 electrons in s. So I've taken care of 4 of the electrons now. So I'm going to take another 2 electrons out, and I still have 3 electrons to place. So I go now to the next arrow. And the next one is 2p. So I write 2p. Well, 2p sublevel can have a maximum of 6 electrons. But I don't have 6 electrons. I only have 3. So I'm just going to put 3 in there, and I'm done. I don't have to go straight to 6. I'm saying I can go up to 6. I only have 3, and that's it. So I've gone 1s2, 2s2, 2p3. This is my electron configuration for nitrogen. All right, like I said, first one might make 0 sense. Let's jump to the next one. Let's jump to manganese, which this is already jumping to a much more difficult one than I would. I'm actually going to do argon first. Let's go to argon. Argon has an atomic number of 18, which means 18 protons, which means 18 electrons. All right, so we start all over again. There we go. We start at the very bottom, 1s. So the beginning of argon's electron configuration is 1s. I can only get 2 electrons in s, so that's 2 of them. Okay? I'm not going to sit here and subtract it out the whole time. I'm going to keep going. Next arrow travels through 2s. So I write 2s down, and s can only hold up to 2. Do I still have 2 electrons? I definitely do. So I have 4 of the electrons. Again, I can add up all the exponents, and that's equal to the number of electrons I've done. Then I go to the next one, 2p. At 2p, do I still have 6 electrons? I guess I should do a little bit of math here. So first energy level, I'm down to 16 electrons left. Second one, I'm down to 14 left. I still have 14. Can I put 14 in p? The answer is no. The maximum I can put in p is 6. So I put 6 there. So I'm going to subtract out 6, and now I have 8 left. So I keep going up this arrow, and my next one is 3s. So I write 3s. I'm back to an s again. I can only get 2 electrons. So that's another 2 electrons out. I have 6 left. So I've done the first 3 arrows, and I haven't filled out 18 electrons yet. I've done 2, 4, 10, 12 electrons. I still have 6 left. So now I move to the next spot. It's 3p. I'm at 3p. P, I can hold 6. How many do I have left? 6. There I go. This is the complete argon electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6. Done. Yay. Okay, you done that one. All right, let's try one more. Manganese. With manganese. Okay, manganese, looking at your periodic table, will have 25 electrons. Atomic number is 25, and protons is 25, so electrons is 25. So let's start speeding this up. I'm going to go through 1s, and s can take 2. I'm going to go through 2s. 2s can take 2. I'm going to go through 2p. P can take 6. I keep going. 3s. 3s can take 2. I keep going. 3p now. 3p is another 6. That's 18 if you remember from argon. But now I got to keep going. I'm up to 4s. S is 2, so 2 more. So right now this is 20 electrons. Kind of helping you out there. I now hit 3d. So I write 3d. Going back to the notes, D can hold up to 10 electrons. I don't have 10 electrons left. I only have 5 more electrons to take care of. So I'm just going to write 5. And that's your electronic configuration for manganese. All right. Sorry, I'm trying to see if we have a periodic table. Okay, I need to pull up a periodic table for us real quick. I'll be right back. All right, so back with the periodic table now. So I want to bring this up to kind of show a little bit that the periodic table is supporting this pattern. Okay, the first two columns, you have two columns here. We're going to call this the S block. Okay, that is the S block, and you can see that there's two columns. So how many electrons can I get in the S block total? Either 1 or 2. Okay. If I go to the other side of the periodic table, the other tall columns, look at how many columns I have here. I have 1, 2, 3, 4, 5, and 6. This side over on this side is called, this side over on this side, this side is called the P block. Okay? And look at that. You have 6 columns. So 1, 2, 3, 4, 5, 6. The whole middle section here, if you count it out, is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's what the D block is. D block can hold 10 electrons. And then guess what? The inner transition metals at the bottom, they have 14 elements. Like if you go across, there's 14 columns, and that is called the F block. So another way to possibly do this, if I try showing like one of these going with it, and you can use the outfall diagram, I just want to show this as well, okay, is if I did something like magnesium, and I said I wanted to do the electron configuration for magnesium, okay? So the way this works is the row number is telling you the energy level you're on, so that big number, and then you change from block to block, and that'll be when you write out which block you're in, which sub-level you're in, sub-shell you're in, all those different words we use for it. So this right here says we have 12 electrons in magnesium. What would happen is I would start right here, and this is one of the early kind of confusing things. Helium is technically part of the S block. It is the S2 part of the S block. So what would happen here is you go across, you don't have magnesium, and so we would fill in whenever you finish a row or you leave a block from S block, P block, D block, you write down the last thing in that block. So this would be 1s2. Then we'd go across this one. This is 2, and this is the S block. I'm leaving it, so I'd write 2s2. I'm entering the 2p block here because I'm in the second row P block. I don't have magnesium still, so I'd write 2p6. And then I enter 3, the S block, and the magnesium's the second element, so 3s2. And that's how you'd keep on going. So this would be 3p, 4s, 3d10. This is where it makes it a little bit more difficult. The D block is one behind the row, so this would be 3d, back to 4p, 5s, 4d, 5p, 6s, and then, I mean, it does get confusing where we go 4F and so forth. So that's where the off-ball diagram does help, where you're sitting there going, why am I going backwards in the middle there? The off-ball diagram is there to help you answer that. Okay, you can use the off-ball diagram, going back to it, to identify that. Okay, so it's helping you figure out that order without you maybe getting a little confused. But the periodic table there is another avenue to go with it. So I'm going to finish up the video there, and I will show the other two notations in one more video to come.